You know, when we picture the Great Wall of China, our minds immediately go to its sheer scale, right? This massive thing you can supposedly see from space. But what if I told you the most mind-blowing thing about it isn't its size at all?
For centuries, how this thing has lasted has been a total mystery. The really fascinating question isn't what it is, but how it is. I mean, how has it survived thousands of years of erosion, earthquakes, even modern construction?
Well, the answer is hiding in plain sight, deep inside its own chemistry. Turns out ancient engineers were absolute masters of material science, and their forgotten recipes completely challenge our modern ideas of what makes a structure strong.
Okay, so to really get into these secrets, we have to get one thing straight. The whole idea of a single continuous Great Wall, well, it's kind of a myth. That iconic gray brick wall you see in all the photos, yeah, that's mostly from the Ming Dynasty. But as you go west, out into the Gobi Desert, the wall just transforms. It becomes this incredible testament to building in one of the harshest, most resource-starved places on the planet.
Each dynasty really left its own unique stamp. The Qin started unifying early sections. The Han pushed way out into the desert, which forced them to come up with some radical new ideas. And then the Ming, they perfected masonry with a truly revolutionary mortar. These different eras gave us two incredible and completely different engineering marvels.
So let's start with the Han Dynasty. Imagine their challenge. They had to extend China's defenses deep into the Gobi Desert, a place with basically no stone and no timber.
I mean, it sounds impossible, doesn't it? And we're not talking about a small fence here. This was a massive fortification. To pull it off, Han engineers didn't invent some new material. They just harnessed what was already there, and in the process, they pioneered a technique 2,000 years before it was invented in the West.
They used something called fascines, which is basically a fancy word for bundles of local desert plants, like the super tough tamarisk shrub and reeds, and they used them as the literal backbone of the wall.
The process is just brilliantly simple. You lay down a layer of these plant bundles, you cover it with sand and gravel, and then you pack it down tight. Layer after layer after layer, they built what is essentially a prehistoric version of what we now call mechanically stabilized earth.
And their choice of tamarisk? It was an act of pure botanical genius. See, soil is really strong when you squeeze it, but it pulls apart easily. Those fine, fibrous tamarisk branches, though, are incredibly strong when you pull them. Some have been measured with a tensile strength of over 270 megapascal.
Exactly. These branches acted just like nature's rebar. They took all that sideways pressure that would normally make an earth wall bulge and collapse, and they turned it into tensile force along the fibers. They were literally tying the wall together from the inside out.
All right, let's jump forward about 1,500 years to the Ming Dynasty. Now they're building those famous stone and brick sections we all know. But they had a totally different problem. How do you create a mortar strong enough to hold it all together, especially in regions that get a lot of earthquakes?
Their solution was so incredibly effective that modern researchers call it one of the greatest innovations of that entire era. And it wasn't a new kind of rock or some fancy mineral. Nope, it was something they ate for dinner.
They invented sticky rice mortar. Seriously, by mixing the soup from glutinous rice into standard lime mortar, they created what was probably the world's first ever organic-inorganic composite material. And the secret ingredient was a complex carb called amylopectin.
This amylopectin stuff from the rice completely changed how the mortar behaved. It actually controlled how the calcium carbonate crystals grew, making the final structure incredibly dense and strong. But, and this is the key, it added a flexibility that pure lime mortar just doesn't have.
And that flexibility meant the mortar could act like a shock absorber. It would bend and deform just a little bit under stress instead of just shattering. Get this, Ming-era tombs and parts of the wall built with this stuff have survived massive earthquakes that totally leveled modern buildings nearby.
And believe it or not, sticky rice was just the tip of the iceberg. Looking at other ancient Chinese mortars, we found a whole chemical toolkit. They were adding things like pig's blood for weather resistance and tung oil for waterproofing. It was an incredibly sophisticated system of construction chemistry. So all of this just begs the question, how do these ancient materials actually stack up against our modern stuff, like Portland cement? Well, the answer is pretty surprising, and it kind of challenges our whole idea of what technological progress even looks like.
This quote really gets to the heart of it. Today, we build for speed. They build for permanence.
The entire engineering priority was just completely different.
Just look at this comparison. Modern cement is unbelievably strong when you compress it, but it's brittle. In an earthquake, it fails, and it fails catastrophically, unless you pump it full of steel. The sticky rice mortar, on the other hand, was inherently flexible. And from a sustainability angle, it's not even a contest. The ancient mortar was made from local, biodegradable stuff, while cement production is one of the biggest sources of global carbon emissions.
So what does all this mean for us right now? Well, it means there are these incredibly powerful lessons in engineering that we've somehow managed to forget.
The engineers of the Great Wall teach us about hyper-local ingenuity, about designing for resilience over centuries, not just a few decades. They show us the unbelievable potential of mixing organic and inorganic materials. They were basically pioneers of green construction, 2,000 years ahead of their time.
It really leaves us with a fascinating thought, doesn't it? As we face huge challenges like climate change and the need for way more resilient infrastructure, maybe the most innovative solutions aren't waiting for us in some high-tech lab. Maybe they're waiting to be rediscovered in the forgotten recipes of the ancient world.